So Stephen Hall is here today. He's an assistant professor and extension specialist in the Department of Plant and Agro-Ecosystem Sciences at the University of Wisconsin-Madison, and he was previously in Iowa. So he's got a lot of knowledge about Midwestern agriculture. So welcome and thank you for coming.
Excellent. Well, I'm learning a lot today, so it's great to be here. As folks that do this kind of work know, grad students are a really key part. So I'd like to acknowledge my PhD student Hariom Yadav, who collected a lot of the data that I'll share today, as well as other co-authors at UW. So Greg Sanford, Adam Von Hayden, and Randy Jackson. So we're going to shift, think a little bit more about soil organic matter, right, and the multiple relationships it has with nitrogen, right? We all know that organic matter is a really important source of nitrogen for crop production. We saw that with all those 0N checks that you guys have been showing this morning. And this is because, right, we think about what organic matter is. Typically, it's a substance on average with a relatively low C to N ratio. So if you look at a whole soil sample, that C to N ratios of 10 are pretty typical. However, this can create a problem, right, when we don't have a crop to take up that nitrogen that's continually being mineralized, right? And so I think we have to think about this, not only our fertilizer management, but also our soil management as something to look out in terms of addressing nitrate leaching. But I think we can also sort of reframe the question, right? Thinking about organic matter as a place to park excess nitrogen if we manage our systems correctly. So today I'll sort of use a long-term experiment that we have in Wisconsin to get at these three issues. And this is against, right, the backdrop of a much larger nitrogen challenge. And so this is a study that some folks did a few years ago, where they tried to estimate what they're calling the surplus nitrogen across the US. And so they're calculating this in a pretty simple way. They go out and they try to find fertilizer data, manure application data, to get a ballpark of how much nitrogen is being applied through agronomic management. Then they subtract off their best estimate of nitrogen removal in the harvested crops, and they get a map like this, right? So where these darker colors are essentially more nitrogen. But really the devil is in the details, right? How you do these calculations. So there was another study about the same time using sort of broadly similar methods, and you don't have to look at the details, right? Just look at the color distributions on these maps. You can tell these are wildly different answers. And so the scientific community, right, really can't agree how much nitrogen are we potentially using, where is it coming from? And there's even a further question, right? You know, not only are there differences in how these numbers are calculated, but they're not accounting for any sort of systematic changes of nitrogen storage in soil. So I'll throw up a third study by some colleagues at University of Illinois a few years ago. But again, you can see not only are these colors different sort of for that overall nitrogen balance, but the absolute magnitude of those numbers are also incredibly different. And you really have to squint. So I'll just tell you, sort of these light yellow areas are places where you might even have a slight negative nitrogen balance up to a small positive number. So suggesting that we're doing a pretty good job of our nitrogen management. Yet, you know, as you know, in many cases, we still have a nitrate problem. So what's the rub? So what we wanted to do was sort of dial in on this overall question of, you know, how much nitrogen are we losing and where might it be coming from, using sort of a unique long-term trial that we have at UW. We wanted to sort of look at a range of different grain and forage cropping systems where we had really good data on nitrogen inputs and nitrogen removal in harvested crops to get at that question of how good is our fertility management in terms of nitrogen sustainability. And the point here is, if we can dial in on what our nitrogen inputs are and what our crop nitrogen removal is, that lets us sort of get a stab at estimating these numbers that are much harder to measure. These, you know, the nitrate leaching and the nitrogen gas losses. And again, sort of to look at, well, what is the role of our soils in sort of, either buffering this nitrogen or actually contributing to long-term nitrogen losses, right? We know that soils aren't static and they are responsive to our management, but it can take a long time before we're able to actually detect changes in the storage of both carbon and nitrogen. And so what we're going to do here is just use conservation of mass, right? I think one of the simple but really powerful opportunities that we have, right? And so all the nitrogen has to add up at the end of the day. If we're not hauling it off the field or storing it in the soil, it's got to be lost from the system. And so we can do some simple math essentially to solve for these environmental losses as the difference between inputs, crop removal, and that change in storage over the long term. And just to sort of give you some simple examples before we actually go through the data, we could think of sort of a relatively simple scenario where our soils are not gaining or losing nitrogen. Maybe we have a corn bean system where we're adding 150 pounds of synthetic fertilizer nitrogen. We get reasonable yields. We might haul off about 120 pounds of nitrogen in grain, so leaving us about 30 pounds of nitrogen left over, right? So if our soils aren't taking that up, right, that nitrogen is available for loss. Pretty typical value for nitrate leaching that we might see in the upper Midwest. So in our second example, right, what if our soils don't actually have consistent organic matter? What if there's actually a long-term trend for decreasing organic matter? So the same sort of fertility management, same productivity, but what if organic matter is decreasing only by 0.1% per year? This would effectively double that nitrogen that's actually available for loss. So give us, perhaps 60 pounds of nitrogen that's leaving the system. So conversely, right, we could have the opposite scenario. Say, we shift to reduced tillage system, or we throw in a cover crop, or we throw in some other mechanism that might allow us to hold on to that extra nitrogen. If we're able to increase soil organic matter by 0.1%, this would effectively wipe out that surplus nitrogen. And so I think really this is sort of the game that we want to be going to. Obviously, we can't increase soil organic matter indefinitely, but I think it's a potentially powerful tool to help us address nitrogen management issues. Okay, so this long-term trial is known as WICST, Wisconsin Integrated Cropping Systems Trial. This is down in Arlington. So this is on a well-drained, lust-derived soil that's just northeast of Madison, if folks are familiar with that area. And this experiment is really interesting and valuable because it's been going on since 1989. It was started by Josh Posner, formerly in our department. The current leads of the experiment are Greg Sanford and Randy Jackson. And so we've got a range of systems, so from continuous corn all the way down to managed rotational grazing of heifers. And these are relatively large plots, so 60 by 500 feet, so you can use relatively realistic farm equipment to manage them. So all of the phases of the rotations are replicated each year fourfold. And these are relatively rich mollisols, so similar to what you all have around here, about 2.5% carbon. No tile drainage, as we'll come back to that later. Okay, so what are these systems? So as I mentioned, continuous corn is one of them. So year over year, chisel plow, synthetic fertilizer. All of these systems, as you imagine, over 30 years, the management has sort of changed subtly as farming practices have changed, sort of informed by broader discussions with farmers and changes in extension nutrient recommendations. The fields are large enough that they're actually each managed as an independent field with respect to soil testing and P and K, et cetera. Okay, so continuous corn, as I mentioned, corn-soybean rotation, chisel plow for corn, no-till for beans. We have an organic corn, soybean, wheat, red clover rotation that gets its nitrogen for corn from a composted poultry manure. And then we've got three forage livestock systems. So we've got a relatively conventional corn alfalfa rotation, so 3 years of alfalfa and corn. So that gets nitrogen from two applications of liquid dairy manure, one prior to corn and then one in the first year of alfalfa. And so this experiment is right across the road from a dairy, and so it works well in that. There is an organic alfalfa rotation, so 2 years of alfalfa and corn, and then finally that managed rotational grazing system that I've talked about. The peppers are rotated among the plots. Okay. So as I mentioned, one of the key aspects of this experiment is that we've got really good historical data on nitrogen inputs, both from fertilizer and from manure. So each time manure is added, several samples are taken and analyzed for nitrogen content. Turns out one of the bigger challenges, right, if you want to do this nitrogen budget exercise, is to get at biological nitrogen fixation. And so we used a yield-based approach to do that. Just sort of a brief digression here. Don't get too hung up on these figures. What we've done is go to the literature and look at relationships between legume yield and nitrogen fixation in the crop. And so we've looked at sort of different scenarios, sort of best estimate, high end fixation, low end fixation. And so we've run the numbers from all of them. Take home point, it doesn't seem to matter too much what we assume for most of these cropping systems, except for the alfalfa. And so we'll get into that a little bit later. Okay, so we've got our nitrogen inputs. Turns out our nitrogen outputs are also pretty well constrained from the crops. So each year we get analyses of so we've got measurements of protein content in all of the grain and the silage and hay that's getting hauled off. So we actually know how much nitrogen is being removed. In terms of the grazing systems, what we're doing is actually weighing the heifers before they, whoop. All right, I'll try to be absolutely still here. So the heifers are weighed at the beginning of the season and the end of the season, and we can actually estimate then how much nitrogen is walking off the plot at the end of the year. So the soils, right? That's perhaps the most challenging part. Thankfully, back in '89, they took really meticulous measurements of soil samples as well as bulk density down to 3 feet. We're using the top 2 feet data here just because there's a little bit more noise. Okay, all right.
So what happened over 30 years, right?
So as you might expect, corn yields have increased. So in our continuous corn and corn bean system, they went from about 150 bushels up to 240 bushels recently. So reasonably productive systems. You'll notice the organic corn, soybean, wheat system always has slightly lower yield, as might be expected. For beans, decently performing beans, consistently above 50 bushels an acre in recent years. Wheat, again, not incredible performer, but close to 75 bushels an acre recently. Okay, so what's unique is we've got the nitrogen removal data. And so we're just taking the yield and the measured nitrogen content, and we know how much was hauled off the field. And what you'll see with the corn, right, that increase in nitrogen removal year over year is less steep than we saw for the yield, right, because the end content of that grain has been dropping. But we're hauling off about 150 pounds per acre in recent years. Soybeans, right, a much higher nitrogen content in soybean grain, and so we're up north of 200 pounds per acre hauled off for that crop. And wheat, obviously much lower on the order of 75 pounds of N per acre. And so remember, what we're doing is trying to essentially calculate a checkbook budget here. So how much nitrogen are we putting in and how much are we removing? And so if that surplus value is going to be up here. If we're hauling off more than we're adding, we're going to be down in this part of the graph. And so you'll notice for these systems, right, there's a lot of variability year to year. If you get poor yields, you can be much higher in terms of your surplus end. But conversely, right, those years where we're busting the bins, we're down here. So we're actually taking off more nitrogen than we're adding to the field. You'll notice this big switch For the green line, that's that organic rotation. So the yields really struggled for a while. So the decision was made to start adding this composted poultry manure. And you can see that switch flip. The yields go up and our partial nitrogen balance also increases. Again, just to remind you, right, we can't run a negative N balance forever. That's got to come from somewhere. It's coming from soil organic matter, right? That's how we can have those negative numbers. And what's interesting, right, in these bean systems, best evidence is that year over year, actually that partial nitrogen balance is negative, right? Because in general, the soybean fixes a lot of nitrogen, but we're also removing a heck of a lot of nitrogen. And so depending on our assumptions, right, we could drag this line a little bit closer to zero, but it's never going to get much higher than it actually is. Okay, finally, the wheat, pretty close to neutral overall, but a lot of variability from year to year. And I'm gonna speed up here as I know we're close to lunch. Okay, so what can you do with this? Well, you can add up all of these numbers year over year to look at how that nitrogen balance has changed. And it's really interesting to look at these different systems. So continuous corn kind of crept along for a while, slightly positive. Recent years, we bumped up the synthetic nitrogen rate, and now we're sort of in consistently positive territory. Corn bean rotation has been trending steadily downward over the 3 decades, and this organic rotation began to stabilize after we added that manure. So we can look at these a little bit different way and look at sort of compare these overall average values for these different systems over time. So what's really, I think, really striking is that if you look at the whole 30-year record and you take the average value, that's what this diamond is on these box plots, you can see that these numbers are pretty close to zero, right? You know, we're about 19 pounds per acre excess in continuous corn. We're -6 for corn soybean, -13 for corn soybean wheat. So suggesting, right, we shouldn't necessarily have a big nitrate leaching problem from these systems. Similarly, we can look at these livestock systems. So the alfalfa corn rotations, you can see the size of this box got much wider. So that's due to the fact that during that corn rotation, we're throwing on a big slug of liquid dairy manure. We tend to be more positive, but we can make that up during the alfalfa phase. If you're taking off 4 cuts of hay, you can run potentially a deficit, but on average, pretty close to zero. Similarly, with the rotational grazing system, just slightly positive, right? That's the nitrogen fixation from the clover. And just, to throw it in perspective, our fertilizer rates, over that 30 years for continuous corn, 144 pounds, that seems pretty low, for recent recommendations, but again, that's that average value over the long term. Similar for corn soybean, 130 pounds on average over that period. For the rotational grazing system, the nitrogen inputs from the fixation are much lower, but then again, the harvest of nitrogen in that heifer biomass is also a lot lower. And then again, the alfalfa rotation, large nitrogen input, but also large nitrogen offtakes in those harvested crops. And so I think, sort of come back to this broader question, right? How much excess nitrogen is actually available for loss? Our results are much more consistent with this study on the right here that was suggesting, maybe, right, if you're managing your fertility, in a reasonable way, your nitrogen balance might be pretty close to zero or sort of a small positive number. So I think, we really need sort of more ground truthing of these sort of large estimates that you see out there in the literature and that are helping to inform policy. So now we come to the soils, and unfortunately, it's a little more depressing. And so if you look at the change in nitrogen over 30 years, most of these systems have actually lost a lot of nitrogen, particularly these soybean systems. So the corn soybean and then the corn soybean wheat. On average, if you compare those stocks of nitrogen from 1989 to 2019, you divide by 30, year over year, you're averaging a loss of about 100 pounds of N per acre per year in these systems. And to a degree, that makes a little bit of sense, right? Because the soybeans are to some extent mining some of that nitrogen, but not nearly as much as this would suggest. The alfalfa systems are doing a little bit better, but still losing a substantial amount of nitrogen, about 50 pounds per acre year over year. One of the big surprises actually is that that continuous corn system on average was pretty close to zero, although it was variable. We have fewer reps for that system just because there aren't multiple phases of the rotation. We've got this one guy down here that's about 100 pounds. The other plots are up closer to zero. The rotational grazing system was the only one that actually gained or tended to gain nitrogen on average, slight gain of nitrogen, although not significantly different from zero. So what does this actually mean if we think about sort of overall nitrogen sustainability? Well, as I mentioned, right, if you just look at our fertility management, I think it's pretty darn good. We're pretty close to zero for all of these systems. So maybe if you just looked at that, you'd say, okay, maybe we don't have a huge water quality problem. But if you look at that combined with this long-term soil change, there's a lot of nitrogen that's potentially available for loss. So if you add up these two graphs that I showed you, you get what's on the bottom, and that's essentially the nitrogen that's available to be lost to the environment, right? We don't know how that's being lost. Could be as gaseous forms in combination with nitrate leaching, but clearly there's substantial nitrogen that's leaving these systems, and at least in this site, it seems that soils are really sort of the dominant mechanism here. But you might say, well, Stephen, these numbers are way too high, right? Is this actually real? And I think we need to sort of drill into this a little bit more. What are actually the implications for nitrate leaching? And so that's what we've been working on recently. As I mentioned, these are well-drained soils, so we can't just use measurements in tile. We have to use some other kinds of approaches. So one thing that we're doing is using these resin lysimeters. These are little PVC pipes with ion exchange resin. Essentially, you can install these. You can dig a soil pit and carve a little pocket into the wall of the pit and stick the lysimeter in and sort of fill it in and backfill the pit. The goal is, right, that drainage will just move through the profile, move through that lysimeter, and then you can come and dig these guys out and extract the nitrate and measure the cumulative leaching over time. So we've worked out some of the method issues. We've done some tracers with potash. So using the chloride in that potash, we were really excited that we get the amount of chloride that we should. So we think that these are a reasonably robust method in these particular soil types. The downside, you need lots of replicates. So we've got 300 of these guys out in the experiment right now. So I'll just share the first year of data. This is from April 24 through April 25. We didn't have enough labor to do this in all of the plots, but we did 4 of these different cropping systems. So the continuous corn, soybean, the conventional alfalfa, and the grazing system. And what you'll notice, right, we have measured nitrate leaching on the order of 50 to 80 pounds of N per acre on average. And so these numbers, these are high, but these are actually consistent with that mass balance that I showed you before, right? And we know nitrate leaching varies a lot year over year. And so this is within the ballpark of what we would expect from those long-term data sets. And again, just to remind you, these values are much higher than that surplus nitrogen input, right? There's no way we could get these numbers simply based on the amount of fertilizer that we're applying and the crop nitrogen removal. So it's really sort of consistent with this overall importance of organic matter as one of the sources of leached nitrate. Okay, so that's sort of the bad news, right? We have to think about sort of these long-term processes going on in our fields in relationship to water quality. But I think, we can sort of flip the script and think about opportunities to actually leverage this nitrogen for crop production. So we did some additional work where we took a whole bunch of these deep core samples across these plots using a Giddings rig. We were really curious in how these systems differed in their capacity to mineralize N, right? If you do this in the field, it's really challenging, super noisy. We saw, some of those data before. Here we're trying to have relatively controlled conditions where you wet the soils up and you let them go for 8 months, and then you look at that difference in ammonium and nitrate before and after the incubation. There's a whole lot more that we did with this, but I'll just focus briefly on that mineral N stuff. We did a lot of work with gases and isotopes that I'm happy to chat about if folks are interested. But one of the really striking points, if we look at sort of the potential nitrogen mineralization from these different cropping systems, it's high from all of them, right? Like as we would expect. Even just the continuous corn and corn bean were about 150 pounds of N per acre. But our alfalfa systems and especially our rotational grazing system were able to double or even triple that N mineralization rate over time. We know, of course, that there is a substantial alfalfa nitrogen credit, but really sort of bringing it home how large this can be in these long-term cropping systems environments where we've been doing these same rotations year over year, because those credits are not just coming from the most recent residues, but also the residues, several years ago, that nitrogen that's sort of slowly moving through these systems. And I think the implication is that we really need year-round living cover and trying to minimize disturbance to actually harness all of this nitrogen that is being slowly released from these systems, especially in these forage livestock systems. So, what can we do about this? I think, this trial was set up in '89 using sort of some of the standard practices at the time. I think there's opportunities to layer conservation practices on now, and that's what my colleague Greg is starting to do for the continuous corn and the corn bean system. And what he's doing essentially is tweaking these. So continuous corn has historically been chisel plowed every year. So he's split the plots in half and he's converted half of it to no-till. He's growing a winter rye cover crop. He's adding manure to the system. Similar story with the corn soybean rotation. Again, an effort to sort of add more organic matter to the system, hold on to that nitrogen that's being released. Again, if we get funding, we'd love to do the same kind of interventions for some of these forage livestock systems. In particular, the alfalfa rotation is really leaky the way we're managing it now. So we're killing off that alfalfa in the fall through multiple tillage passes, right? The soil's bare until spring. When we throw on the liquid dairy manure in the fall as well. So it's kind of not necessarily the optimum for retaining those nitrogen inputs. So the thought is to move to a reduced or no-till system for that alfalfa rotation, planting green, and actually applying the manure to a system with living plants to actually better enable retention of that manure. Also, we're excited about opportunities to actually apply some of the excess manure to these grazing systems, right? Manure management is the huge challenge, finding out places to distribute that where we can actually keep it in the system as opposed to losing it. So essentially, that's what we've been up to. I think that key take-home point, right? We absolutely need effective nitrogen fertility management to deal with nitrogen leaching, but that on its own is not always sufficient. Oh, sweet. Okay. I think I sped up. So good. We've got plenty of time. All right. Yeah. So fertility management necessary, but not necessarily sufficient to address nitrate leaching, simply because we've got to take into account what our soils are doing, right? How much nitrogen they might be releasing. So thinking about practices that can enable us to hold on to that nitrogen that's trickling out slowly and actually putting it to use growing crops, right? Rather than have it leak out the bottom of the system. But I think more than that, right? So this is just one, it's a great study, but it's in one place in South Central Wisconsin. I think we really need to think more critically about, sort of these longer term changes in soils in our region. It's really challenging to actually get those robust measurements of how carbon and nitrogen are changing over time. Thinking about, the whole soil profile, taking into account how bulk density is changing. And I think we really need more studies to get a sense of whether these losses of organic matter are normal or whether this is just something strange about our site. I don't think it is, right? This is sort of a, very ordinary cropland in south central Wisconsin that was managed under a dairy rotation for many decades prior to the experiment that started. But again, sort of provocative of whether this is normal or whether other places are losing nitrogen over time as well. So this really fortunate sort of walk into this data set. And so this is really building on the shoulders of giants and many folks that actually did this work over the decades, and whole boatload of funding sources. If you're curious about our nitrate leaching approach, we recently came out with an extension article that sort of describes those resin lysimeters and a sort of a number of other low cost and higher cost ways of measuring nitrate leaching in these well-drained soil systems where you can't just measure the tile drainage. So putting in a plug for that. We also have a nitrogen budget calculator that's up online, looking to sort of further refine that. But I think encourage everyone to think about doing that kind of basic math for their systems, right? How much nitrogen are we putting on? How much nitrogen do we think we're taking off? It's not always a bad idea to think about taking some of your grain samples and actually getting nitrogen measurements to get a sense of that nitrogen balance on your own croplands. So I think we've got time for questions, but I know we also have lunch coming up. But yeah. And let's see, I guess there's that Slido. Yeah, any gaseous loss measurements? Great question. So a variety of different folks have worked at WIXT measuring various nitrogen gases over the years. There are some folks that are measuring N2O. Typically, that's a very small component of the N budget, like really important for its climate impact, but sort of almost a rounding error in terms of the nitrogen balance. Probably the largest gaseous loss would be ammonia. Of course, in these systems, that's really a beast to measure. So definitely merits measurement in the future. Dinitrogen gas is also probably important in these systems, but again, very difficult to measure. So we have a question about the resin lysimeter. Yeah, someone was paying attention. That's great. And so they notice that the resin lysimeter data was different for continuous corn than the other systems. That's a great point. And so if maybe what I'll do actually, since we have a little time, I'll go back and look at a slide here and find it. The interesting thing about the continuous corn is that we bumped up the nitrogen rate relatively recently. And so essentially, this has been trending upwards recently. However, if you take the full 30-year data set, it's not too bad. But if you were just to use the past 10 years, this number would be much higher. We also have relatively small change in soil nitrogen in that continuous corn system. However, there's a lot of variability, and there's this guy that's down at 100. And so I think we really have low power to detect changes in that corn system just because we have fewer plots. And so then when we go and actually look at the measured values of nitrate leaching, what you see, this is among the highest, but it's also got the highest error bar. So again, I think all of these things are sort of compatible with each other, right? We've been bumping up the nitrogen rate year over year. There doesn't seem to be a huge change in the soil nitrogen stock, but a lot of variability. And two, right, we know every year is different in terms of nitrate leaching. This might have been a bad year, as we know, like spring of 24 was pretty wet. It was wet for you all. It was wet for us. It was sort of ideal conditions for leaching, given that 23 was pretty dry late into the year, at least by us. I think it was for you all also. So there was a lot of legacy nitrate that probably got flushed early in 24. So that's one potential explanation. We've got more data rolling in. We'll have We're about to go dig out the lysimeters this April, so we'll have another year to add.
Are those dug out annually?
Yes, that's a great point, right? You could do this different ways. I think we're most interested in those annual totals. If we were really ambitious, we could go and pull them out seasonally, but we just want to minimize the disturbance to the extent possible. And again, if we're able to get additional funding, we'd love to be able to do some more sophisticated lysimeters. So equilibrium tension lysimeters, where you can sort of adjust the tension of the lysimeter to match the matrix potential. Those have worked really well in these systems, but they're just very, very expensive. But we'd love to throw some of those into the mix as well. Let me go back to the slide here. Whoa, any other ones? What else?
Ben, go ahead.
Yes, one question. The last graph you showed us showed that you were converting over to a corn silage and a corn silage soybean. Aren't you concerned about losing organic matter with those systems?
Yes, so that's a great. Oh, I'll repeat the question. So looking at sort of the new split plots on top of that, and this is one question. Since in the past, silage has been taken from portions of those plots and grain has been taken from other ones. It's true, right? If you remove those above ground residues, you're removing that source of organic matter. However, if you're going to no-till in those systems, there's a lot of debate in the literature about how actually important sort of those residue inputs are versus sort of below ground contributions. And the thought is maybe you could make it up with the cover crop. But you're right, that's actually part of the experiment is actually to look at that explicitly if you compare residue removal systems versus non-residue removals. But thanks again for that sharp eye at that slide. Yeah.
Other questions?
I was wondering about the fact that other than the only corn system, the one that seemed to have the most impact was the forage and grazing only section. How do you think the animals that graze would have impacted it? And also about the type of animals, because there are certain animals that will pull for instance, grass from the roots, such as goats, rather than simply clipping grass, such as cows.
Yeah. So the question was about disturbance in the managed grazing system. So these are essentially managed through rotational grazing. So essentially they're in small paddocks, and the herd is moved from paddock to paddock based on the standing height of vegetation to avoid overgrazing. So that's an explicit consideration. Yeah, we're trying to avoid those situations of overgrazing. And again, it's like in these systems, there's not evidence of overconsumption of the grass. But yeah.
Stephen, you gonna be with us the rest of the day?
Yep, I'll be sticking around. So happy to chat with folks that'd like to visit. And yeah, one more. Yeah, great.
You noticed that you were putting manure on front corn after alfalfa, and how much available land and total land was in that, and do you think it's necessary? I realize the study started 35 years ago.
Absolutely, that's a great point. And so, with respect to the manure management in relationship to corn, I agree. Right, we're not, I think, adequately taking account for the nitrogen credit from the alfalfa. I think potentially putting on the manure at the wrong time, and that's again what we'd love to sort of explicitly test, split that plot, change that strategy. But again, that was sort of business as usual in the late 80s. But clearly folks have changed practices, and we'd love to be able to document those effects. Yeah.
Thank you.
Great. Well, thanks.